Hello friends, good afternoon and welcome to EduSat live lectures. Dear friends, today in physics we will talk about quantum nature of laser. In that we will talk about laser and its applications. To discuss this topic we have with us our subject expert Dr. Sonia Bansal. Dr. Bansal is assistant professor in YMCA University of Science and Technology, Faridabad. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Today's topic is quantum nature of light, where we define the various quantum mechanisms, various quantum phenomena to explain the laser. First we start the quantum nature of light. In the quantum mechanics, the word quanta basically is a very important word which comes from the 1900, explained by the Max Planck, which explained that the quanta consists of discrete bundles or chunks of energy h nu. In 1905, Einstein redefined the quantum hypothesis and gave the name photon to that quanta, to the quantum of light energy, which is equal to h nu. The photon represents minimum energy unit of light. It is localized in the small volume of the space and remains localized as it moves away from the light source. Hence, the energy of photon is defined by E, which is equal to h nu, which is known as a quanta or known as a photon. Light energy rho nu emitted by the source must be integral multiple of the photon energy, means rho nu is equal to nu is equal to n h nu, n may be 1, 2, 3 and so on. The interaction of the radiation with matter is better explained using the concept of photon rather than by using the wave concept. Basically, there is an energy exchange can take place only at a certain discrete values for which the photon energy is the minimum energy unit that light can give or accept. Mean there is a transmission and there is a absorption. Wave picture of the light is classical phenomena and the photon picture is a quantum phenomena. Laser is inherently a quantum mechanical device because its operation depends on the existence of photon. Without quantum mechanics, laser cannot be explained. Now, first to define the quanta, we define the interaction of the light with the matter. Maxwell defined the light belongs to a group of electromagnetic waves propagating with the speed c in a vacuum, and the frequency and the wavelength related to c through c is equal to nu lambda. When incident on the substance may undergo reflection, transmission, absorption and scattering to varying degree depending on the nature of the substance. Basically, there is a result in loss of energy and hence decrease in the light intensity with the distance, that is the absorption or known as the attenuation. Here input wave is going in the absorbing medium and this is a medium which absorbs the light, and the output wave is the loss of the energy. Attenuation of the light is an absorbing medium. Attenuation is defined by the attenuation coefficient alpha, which is a measure of the absorption of light in an optical medium. Here this is the optical medium and the absorption of the light takes place, and that is defined by the alpha. And what is the intensity of light? If we consider that how attenuation we will get, intensity of light I at any distance x in the medium is defined by I is equal to I naught e power minus alpha, which is the absorption, into x. X is the distance up to which the light is absorbed in the medium. This is the absorbing medium in the diagram, and this side is the air. Light is coming, I naught is the incident light which is absorbed by the medium, and this is I. Then I intensity, absorbed light is defined as I naught e power minus alpha x. Light intensity decreases exponentially with the distance in the medium. As the distance increases, the intensity of light automatically decreases. When the light beam encounters obstacles which have sizes smaller than the wavelength, means the size of the absorbing medium less than the size of the wavelength, means d is less than, very less than equal to lambda, it is redirected into different direction. That is known as the scattering. Light takes place in the form of the scattering. Scattering phenomena also causes attenuation of energy and is described by the exponential law, which is equal to I is equal to I naught e power minus alpha s. S represents the scattering and x is the distance up to which light can be absorbed or can be scattered. Alpha s is the scattering coefficient. Attenuation of light due to both absorption and scattering effect is defined as I is equal to I naught e power minus alpha a, this is because of the attenuation or absorption, and plus alpha s, which is the scattering factor, and x is the distance up to which light is absorbed and scatters. And what is the intensity? Intensity will automatically decrease. Now, what is the distribution of the atoms? Distribution of atoms is defined by the between the energy levels. There are the two states, ground state and excited state. Energy level basically permitted orbits which with specific amount of the energy. Here we define the ground state in the diagram. Ground state as the excited state is defined as n is equal to 1 is the ground state energy level, n is equal to 2 is the first excited state, n is equal to 3 is the second excited state, and so on. And this part is defined how the energy is changing, how the energy is increasing, and this part defined as the orbit, electron orbit diagram. We represent the center part is the nucleus and others are the excited state, and one is the ground state and other are defined the higher excited state. Then ground state and excited state, what is a population? Population means number of atoms per unit volume that occupy a given energy state. Population n of an energy state depends on the temperature T according to Boltzmann equation, then that is defined as n is equal to e power minus E divided by kT, where k is the Boltzmann constant. Atom distributed differently in different energy states tend to be at the lowest possible energy state. At the ground level, molecules are maximum. As the energy given to the ground state, the molecule excited to the higher state. What is a thermal equilibrium? At temperature about 0 Kelvin, atom always have the some thermal energy and distributed among available energy levels according to their energies. At thermal equilibrium, population at each energy level decreases with the increase of the energy level. At the ground level, population is more. At the excited state, first excited state, population is less, and the second excited state is very less, and so on, it will be decreased. Here in the diagram we see that as the energy increases, the population decreases. Population defined by N1, energy of the state defined by E1. For the second state, for the energy state, energy is E2 and population of that state is N2. For the energy level E1 and E2, the population can be computed by the Boltzmann equation. For the first level, for the level 1, the population N1 is defined as is equal to E power minus E1 divided by KT. E is the energy level, and N2 is equal to E is equal to minus E2, energy of the second state, divided by KT. The ratio of population means there is a relative population for N2 by N1, which is defined by E is equal to minus E2 minus E1 divided by KT, or we can write it as N2 is equal to N1 E power minus delta E divided by KT. Delta E is equal to E2 minus E1. Hence, the relative population N2 divided by N1 dependent on the two factors. Number 1 is the energy difference E2 minus E1 of the two levels, and second is the temperature. Temperature define the relation between the population of the two states. At room temperature, if you consider the room temperature, all the atoms are at the ground state. If the temperature increases or at the higher temperature, atoms moves to the higher state. In the material, at thermal equilibrium, more atoms are in the lower energy state than in the higher energy state. The fraction of atoms would be larger if the energy levels are close or temperature is large. As we increase the temperature, the population at the upper level will be more as compared to the ground level. In the limiting case, when E2 minus E1 is equal to 0, it means population of both the levels are equal, N2 is equal to N1. When T approaches to infinite, the similar condition is there, N2 is equal to N1, population of two states are equal. From this we can say that as long as the material is in thermal equilibrium, the population of the higher state cannot exceed the population of lower state. It means by using this we can define the excitation and de-excitation. If the molecules are at higher level or the atoms are at the higher level, then it will be excited and it may be de-excited. Excitation. What is excitation? Electron in the ground state receives an amount of energy equal to the difference of energy of ground state and one of the excited state, and absorbs energy and jumps to the excited state. Means here in the diagram you see, in the diagram B, we can see that there is a two state, E1 and E2. And all the molecules are at the lower level, means at level E1, and they absorb the energy which is equal to h nu, and they excite it to the higher state, and the higher state is populated. It means there is a excitation take place. The photons of energy h nu is equal to E2 minus E1 induce electron transitions from energy levels E1 to E2, that is known as the induced or stimulated absorption. In the diagram A, we can see that this is the ground level in the orbit, ground orbit, and this is the higher orbit. Then electron is jumped from lower orbit to the higher orbit, means electron is excited to the higher state. And here in the diagram second, it is at the higher level and it is de-excited to the ground level by emitting the photon. The electron cannot stay in the excited state for a longer time. It has to get rid of excess energy in the order to come to the lower energy level. Only mechanism is through emission of a photon. Or what is the de-excitation? The excited electrons emit a photon of energy h nu, which is equal to E2 minus E1, and jumps from the excited state to the ground state, and that is known as the spontaneous emission, that is done automatically. The electron in the higher state jumps to the lower state by releasing some energy. To define the absorption and emission, the Einstein give the prediction. In 1917, Einstein predicted that there must be a second emission process to establish thermodynamic equilibrium. What was it? It was a stimulated emission. Atoms move to the excited state under the action of incident light. Excited atoms tend to return randomly to the lower energy state, that is defined by the spontaneous emission. It is likely that a stage may be reached when all atoms are at the excited state. Violation of thermal equilibrium condition is defined here. Einstein suggested that there could be an additional emission mechanism by which the excited atoms can make downward transitions. Prediction that the photon in the light field induced the excited atom to fall to the lower energy state and give up their excess energy in the form of photon, and that is known as the stimulated emission. There is a three process according to Einstein. Define the three process now. First is consider a medium consisting of identical atoms in the thermal equilibrium having energy levels E1 and E2. Here this is the energy level E1, this is the energy level E2, and the population of energy level E1 is N1 and population of energy level E2 is N2. The first process is the absorption, where the atoms in the lower energy level E1 absorbs the incident photon and jumps to the excited state E2. Here this is the energy levels, and electrons absorb the energy of photon h nu and jump to the higher state, and which is defined by A plus h nu, and it is on the excited state, that is defined by the A star. This is known as the induced or stimulated absorption. What is the rate of absorption? Where R rate of absorption is equal to B12 rho nu N1. N1 is the number of population and population of the lower level, and rho nu is the energy density of the incident light to raise the atom to the excited state, which is absorbed by the electron. And B12 defined as a constant of proportionality known as the Einstein coefficient for induced absorption. It indicates the probability of an induced transition from the level 1 to 2. Second process is the spontaneous emission. Spontaneous emission, and excited atoms can stay in the excited level for an average lifetime that is defined by tau sp, lifetime for the spontaneous emission. It is not stimulated by any other agent during this short stage. Electrons now at excited state. Excited atom undergoes a transition to the lower energy level at its own by giving the excess energy in the form of photon. This h nu is equal to E2 minus E1. This is the emitted photon. Then A star is equal to A plus h nu. This is known as the spontaneous emission. This extra term because it is releasing the energy, releasing the photon of h nu. Rate of spontaneous transition is defined as RSP. Here the one term is missing, which is rho nu, because here we are not giving any extra energy to jump the electron from higher state to the lower state. It is automatically comes from higher state to the lower state. Then define rate of spontaneous transition. RSP is equal to A21 N2. N2 is the population of the state 2. What is A21? A21 is the Einstein coefficient for spontaneous emission and is a function of frequency and properties of the material. Probability of spontaneous transition from level 2 to 1. A21 is equal to 1 by tau sp, which depends upon the lifetime of the excited state, which is represent the lifetime of spontaneous emission also. What are the important features of spontaneous emission? No outside control is there, probabilistic in nature, incoherent light we receive, not monochromatic light we receive by the spontaneous emission. There is a lack of directionality. Incoherent radiation, here in the diagram there is not a coherent, and we cannot get the laser output by using this spontaneous emission. Incoherent radiation means result from the superposition of the wave train of random phases. Net intensity is proportional to the number of radiating atoms, means I total is equal to Ni, N is the number of radiating atoms. And see in the diagram, this is a component waveform, and these are not in these all are in random. So dominates in the conventional light source. Next, and the important part is the third process is the stimulated emission. An atom at the excited state here, and it has to wait for the extra energy to stimulate it. An atom in the excited state need not to wait for the spontaneous emission to occur if a photon with the appropriate energy h nu is equal to E2 minus E1 interact with the excited atom. It can trigger the atom to undergo transition to the lower level and to emit another photon. In the diagram we can see that this is the energy level E1, this is energy level E2, electron or the atoms are the higher state, and at this state the stimulation of the atom takes place and the atom will jump to the lower state and then emit the photon, not the single but the two photon of the energy is released, and they are all in phase. The process of emission of the photons by an excited atom through a forced transition occurring when the influence of the external agent is called the induced or stimulated emission, which is defined by the equation A star plus h nu. Here the term h nu is addition because here energy is given to the atom to jump from higher state to the lower state or to stimulate the atom, and is equal to A, which is equal to 2 h nu, means 2 photon will be released. Now we define the rate of stimulated emission. RST is equal to B21, which is the Einstein coefficient for the stimulated emission, rho nu energy density, and N2 is the population of excited state. What are the important features of the stimulated emission? This is a controllable from outside, means we stimulate the atom to jump from higher state to the excited state. Second important point is emitting photon propagates in the same direction as that of the stimulating photon, have exactly same frequency, phase and plane of polarization. Light produced in directional, coherent and monochromatic. These are the characteristics of the laser light. By using the stimulated emission, there is a light amplification takes place. What is a light amplification? Means amplification of the light means intensity will be high. Multiplication of the photon takes place here. Here we see that one photon release the two photon release the more photon, and more photon release the more photon, and in this manner there is a equation 2 power 0, then 2 power 1, 2 power 2 and so on up to 2 power n photons will be generated. Multiplication of the photon takes place all in phase and travel in the same direction, so that lasing action can be take place. All the coherent waves interfere constructively so that we can get the high intensity, and resultant amplitude is continuously growing. Result is amplified light takes place and we can get the high intensity. What is a high intensity? Because of the constructive interference of the wave, net intensity of the resultant light is proportional to the square of the number of atoms emitting light, which is defined as I total is equal to n square into I, which define the high intensity light. What are the steady state condition? In the spontaneous emission, all the three processes occur together with a balance between the absorption and emission to get the laser light. Here we see that the excited state with the population density N2, this is the normal state with the population density N1. Absorption and emission process in the steady state of the material. Here this process is the absorption, atoms excited to the higher state by getting some energy, and then it spontaneously comes to the lower state by releasing some energy which are not coherent, and then when stimulate the atom at the higher level, the stimulated emission takes place by releasing the extra energy. At thermal equilibrium, spontaneously emitted photon can induce stimulated emission from another excited atom. It is also likely to be absorbed by the lower level atoms, and higher probability because of the larger population of the N1. Einstein defined this relation to explain the absorption and emission phenomena, that is defined by the Einstein relation. Define the two condition under the thermal equilibrium condition, means population N1 and N2 in the lower and upper energy levels must remain constant. This condition requires that number of transition from E2 to E1 must be equal to the number of transitions from E1 to E2. It means number of atoms absorbing photon per second per unit volume must be equal to the number of atoms emitting photons per second per unit volume. Absorbing and emitting will be equal. Then from the previous equation we solve for the absorption, which is equal to B12 rho nu N1 is equal to here the emission, then we consider both the emission, spontaneous emission as well as the stimulated emission. Then we take first the spontaneous emission, which is whose equation is A21 N2 plus this is the stimulated emission, which is B21 rho nu N2. Now consider rho nu this side and we take B21, this equation we will take that side, then we have B12 N1 minus B21 N2, which is equal to A21 N2. Now here we calculate the current density, which is rho nu is equal to A21 N2 divided by B12 N1 minus B21 N2. Dividing both the numerator and denominator on the right hand side with B12 and N2. Then rho nu is equal to A21 divided by B12 and N1 divided by N2 minus B21 divided by B12. This is defined by the equation number 1. As we know, N1 divided by N2, ratio of the population of the two states, which is equal to e power E2 minus E1, difference of the energy of two states depends upon the temperature also. K is the Boltzmann constant and T is the temperature, which we can define as e power h nu divided by kT. Now density, current density defined by A21 divided by B12, 1 divided by e power h nu divided by kT minus B21 divided by B12. Here we put the value of N1 by N2 here. Now to maintain thermal equilibrium, the system must release energy in the form of electromagnetic radiations. It is required that the radiation be identical with black body radiation and be consistent with the Planck's radiation law for the any value of T. From that we consider this equation. According to the Planck's law, the radiation density is defined as rho nu is equal to 8 pi h nu cube mu cube divided by c cube into 1 by e power h nu divided by kT minus 1. How many oscillators are absorbed by the molecule? Then mu is defined as refractive index of the medium and c is the velocity of light in the free space. By using this equation, we solve the above equation where the energy density rho nu derived will be consistent with the Planck's law only if B21 is equal to B12. Then B21 divided by B12 is equal to 8 pi h nu cube mu cube c cube defined by the equation number 3b. If these two are equal, then we can write it here. Then B12 is equal to B21. This equation will be c cube divided by 8 pi h nu cube mu cube A21, which is equation number 4. Equation number 3rd A and 3rd B are known as the Einstein relation, and equation number 4 gives the relation between the A-B coefficient. Equation number 3rd A, coefficients of both the absorption and stimulated emission are numerically equal, as B21 is equal to B12. When an atom with the two energy levels is placed in the radiation field, the probability for the upward absorption transition is equal to the probability of downward transition, means stimulated emission and absorption are equal. Equation 3rd B, this equation which defines the ratio of the coefficient of spontaneous versus stimulated emission A21 divided by B12 is equal to third power of the frequency, which is equal to nu cube, third power of the frequency of the radiation. This is why it is difficult to achieve laser action in the higher frequency range such as X-rays, because of the ratio of the spontaneous versus stimulated emission. The condition should satisfy, which is equal to nu cube. What are the conditions of the large stimulated emission? Key to action, laser action, which leads to the laser action. Then Einstein defined the laser stimulated and absorption condition. On the basis of that, some laser condition can be defined. Now, what are the key to the laser action? Existence of stimulated emission define the laser. In practice, absorption and spontaneous emission always occur together with the stimulated emission. Determine the condition under which the number of the stimulated emission can be made larger than other two processes. Ratio of the stimulated transition to the spontaneous transition, that will be defined by the R1. R1 define the stimulated transition divided by the spontaneous transition. Both the equation defined here, and then using the value of rho nu from the Planck's law, we get R1. The value of R1, which define the ratio of stimulated transition to the spontaneous transition. From the Einstein relation, we have is equal to C cube divided by 8 pi h nu cube and mu cube. Welcome back. We are defining the condition of large stimulated emission, where we are using the Planck's radiation law as well as we are using the Einstein relation. By using the Planck's radiation law, we put the equation in the Einstein equation. Then we find out that what is the ratio of the stimulated emission to the spontaneous emission. Then R1 defined by the ratio of the stimulated transition to the spontaneous transition, B12 by A21 rho nu, where N2 is cancelled here. Using the value of rho nu from the Planck's law, we know that R1 is equal to B21 A21 8 pi h nu cube mu cube divided by C cube into 1 by e power h nu divided by kT minus 1. From the Einstein relation, we have B21 divided by A21, or we can write it as B12, as B21 is equal to B12 divided by A21, which is equal to C cube divided by 8 pi h nu cube mu cube. We put this equation in this R1, then we can have, then R1 is equal to C cube divided by 8 pi h nu cube mu cube and 8 pi h nu cube mu cube divided by C cube into 1 by e power h nu divided by kT minus 1, which is equal to 1 by e h nu by kT minus 1. Means R, if we consider the spontaneous to stimulated emission, then we have the 1 by e h nu divided by kT minus 1. If we assume the value of frequency is equal to 5 into 10 power 14 hertz, then of the yellow light, then or temperature which is equal to 2000 Kelvin, the value of h nu divided by kT is 11.99, and we put this in equation. Then we have R1 is equal to 1 by e power 11.99 minus 1, and R1, the value of R1 is equal to 6 into 10 power minus 6, which shows that in the optical region, spontaneous emission dominate over the stimulated emission. For the larger number of the stimulated emission, the light field density rho nu present within the material is required to be enhanced. Hence, the ratio of stimulated transition to the absorption transition is defined by R2. Here we define the stimulated transition divided by absorption transition by the equation B21 rho nu N2 divided by B12 rho nu N1. N1 and N2 are the population of the two states. As we know, B21 is equal to B12, then we can write R1 is equal to N2 by N1, means the stimulated transition towards the absorption transition is number of population of the two states. At thermal equilibrium, N2 minus N1 very less than equal to 1. Then absorption transition overwhelm a stimulated transition. A photon of light field on hitting the medium has a much higher probability of being absorbed in the ground state than that of the stimulating and excited atom. If on the other hand N2 is greater than N1, means population of second level or excited level is higher than that of the ground level, the photons are more likely to be cause stimulated emission than absorption. Therefore, in order to achieve the more stimulated emission, the population N2 of the excited state should be made larger than the population of ground level or the lower energy state. Two conditions to be satisfied for the stimulated emission to overwhelm the spontaneous emission. Number 1, the population of excited level should be greater than that of the lower level. And the second condition is the radiation density in the medium should be very large. Then what are the conditions of the light amplification? A beam of light propagating through a medium may absorb or produce more photon that will be amplify and produce the amplification of the light. Since the probability of the absorption and stimulated emission are same, both attenuation and amplification of the light beam occur simultaneously. Amplification can predominate only if there are more atoms in the higher level than that of the lower level. As the beam travels through the medium, some photons are absorbed due to the absorption transition and some photons are generated due to the emission transitions. Let alpha be the absorption coefficient of the medium, then intensity I after the travelling distance x in the medium is defined by I is equal to I naught e power minus alpha x. X is the distance up to which the light can be attenuated or absorbed. Light intensity decreases exponentially with the distance of the medium. Now, absorption coefficient alpha can be related to the difference in the populations N1 minus N2 of the two states, energy states, by computing the net loss of photon from the light beam, which is difference between the net rate of absorption and stimulated emission transition, which is defined by alpha is equal to N1 minus N2 into B12 h nu divided by V, where V is the velocity of light in the medium, which is equal to C divided by mu. For a material in the thermal equilibrium, then N1 population at the lower level is greater than N2 and the alpha is positive, attenuation is positive. Then if the N2 is somehow made generated greater than that of N1, then alpha becomes a negative quantity and the relation takes place in the form of I is equal to I naught e power minus alpha and is equal to I naught e power x. Then where gamma is equal to minus alpha. Here put the gamma in place of the minus alpha, which is defined as the gain coefficient per unit length. As the gain coefficient gamma is a positive quantity, the relation implies that intensity grows exponentially as the light beam travels through the medium. This is clearly amplified of the light and is defined as gamma is equal to N2 minus N1 B12 h nu divided by V, which is a condition for the amplification of the light, where gamma will be positive, and if gamma only positive and N2 minus N1 greater than 0, means population of higher level is more as compared to the population of the lower level. Condition is known as the population inversion because it is inverse of the normal situation. The condition for gamma that the population inversion is a necessary condition to be satisfied for causing the amplification of the incident light. Now, what is the population inversion? Population inversion is defined to achieve the higher molecules at the higher level. The laser operation requires obtaining the stimulated emission exclusively. To achieve a higher percentage of the stimulated emission, a majority of atoms should be at higher energy level than that of the lower level. The non-equilibrium state in which the population N2 of the upper level exceeds to the larger extent than the population of lower level, this phenomena is known as the state of population inversion. Extending the Boltzmann distribution to this non-equilibrium state of Pi, it is seen that N2 can exceed N1 only if the temperature will be negative. Now, here is a concept of negative temperature. The state of population inversion is sometimes referred to as a negative temperature state. Does not mean that we can attain the temperature below the absolute zero. It implies a non-equilibrium state. Negative temperature are defined only for the non-equilibrium state. Population inversion state is attained in normal temperatures also. For a system that has the 3 state E1, E2 and E3 in the equilibrium, the uppermost level E3 is populated least and the lowest level E1 is populated most. Here we see population in the equilibrium state. In the diagram we can see E1, this is the lowest state which is highly populated, and the second state E2 which is less populated, and this is less populated. And this is a condition for the population in the equilibrium state. Since the population in the 3 state is such that N3 is less than N2 is less than N1, the system absorbs photons rather than emit photons. If the system is supplied with the external energy such that N2 exceeds N1, the second diagram B, we can see the population inversion of E2 with respect to E1. Now, energy is given to this state and the electron at this state is more as compared to the lower state. Then system reaches population inversion, and population inversion takes place between these two levels N1 and N2. Under the Pi condition, stimulated emission can produce a cascade of light. The first few randomly emitted spontaneous photon triggers stimulated emission of more photon, and those stimulated photon induce still more stimulated emission, and so on. As long as the excited state population is more than that of the lower level population, then stimulated emission are more likely than the absorption, and consequently light gets amplified. Our main purpose to amplify the light to achieve the more population inversion. By population inversion, we can amplify the light. Here in the diagram, we see that the input wave, here very less amplified wave in the medium, if amplify means N2 is greater than N1. In the previous diagram, we see that N1 is greater than N2, but in this diagram, we see that N2 is greater than N1. Number of population at the higher level is more as compared to the population of the lower level, and the light is absorbed by the molecules and it will be amplified, and then output wave is more. The intensity of output wave is more as compared to the intensity of the input wave. Here the amplification of the light takes place. The moment the population of lower level becomes equal to or larger than that of the excited state, then Pi and stimulated emission diminish and amplification of the light ceases. How it can be possible? It can be possible by the mechanism pumping. How we can achieve the population inversion at the higher level? We excite the more atom to the higher level by some means. Means more electrons will be absorbed at the higher level by using the pumping. The process by which the atoms are raised from the lower level to the upper level is known as the pumping. The energy is to be supplied somehow to the laser medium to raise atoms from the lower level to the excited level, and for maintaining population at the excited level at a value greater than that of the energy level of the lower state. Usual method is the heat the material. Heating the material only increases the average energy of the atoms but does not make N2 greater than N1. Pi cannot be achieved by heating the material. Then what are the processes? There are different processes to achieve the pumping methods. To create the state of Pi, population inversion, selectively excited the atoms in the material to the particular energy level. Most common methods of pumping make use of the light or electrons. First pumping process is the optical pumping, where we use the photons to excite the atoms. A light source or a flash lamp discharge tube used to illuminate the laser medium. Photons of appropriate frequency excite the atoms to the uppermost level. Atoms drop to the metastable level to create the state of population inversion. Optical pump source may be flash discharge tube, continuously operational lamps, spark gaps or auxiliary lasers. Optical pumping is suitable for laser medium transparent to pump light. Optical pumping is used for solid state crystalline and liquid tunable dye lasers. Second is the electrical pumping. Electrical pumping can be used in case of laser material that can conduct electricity without destroying laser activity, means limited to the gases. In case of gas laser, a high voltage pulse initially ionizes the gas so that it conducts electricity. An electric current flowing through the gas excites atoms to the excited level, from where they drop to the metastable upper laser level, leading to population inversion. Direct conversion takes place also in semiconductor lasers. Also, electrical pumping is used, but there is not the atoms that are excited. It is current carriers E, H power n minus H, electron pairs which are excited, and population inversion is achieved in the junction region, where we use the hole and electrons used for the pumping process at the barrier level. Electrons recombine with the holes in the junction region, producing laser light. Thus, a direct conversion of electrical energy into light energy takes place in the semiconductor laser, and holes and electrons are used for the pumping. Now, active material which is the basic need for the lasing action. All types of atoms are not suitable for the laser operation. There are some selective material in the medium consisting of different species of atoms. Only a small fraction of the atoms of a particular species are suitable for the stimulated emission and for the laser action. Those atoms which cause light amplification are called the active centers, where the light excitation and emission of the electrons takes place. The rest of medium acts as host and supports active centers. The medium hosting the active centers is known as the active medium. An active medium is thus a medium which, when excited, reaches the state of population inversion and eventually causes light amplification. The active medium may be solid, liquid or gas, depending upon which type of laser we are constructing. Now, the most important part is the metastable state to get the lasing action. An atom can be excited to the higher level by supplying the energy to it. Normally, the excited state have the short lifetime in the form of nanoseconds, means 10 power minus 9 seconds, and release their energy by the spontaneous emission. Atoms do not stay at such excited state long enough to be stimulated to emit their energy. So, the pumping agent continuously raises the atoms to the excited state, and many of them rapidly undergo spontaneous emission, and population inversion cannot be achieved. For establishing population inversion, the excited atoms are required and have to wait at the upper level. So, the lifetime of that level should be more as compared to the other level, so that the electron can relax at that level more as compared to the other level. Then what is the need an excited state for a longer lifetime? Such longer lived upper levels from where an excited atom does not return to the lower level at once, but remains excited for a appreciable time, which is known as the metastable states. Then what is this state? Atoms stay in the metastable state for about 10 power minus 6 to 10 power minus 3 second. This is 10 power 3 to 10 power 6 times longer than that of the atoms of the other excited state. Possible for the large number of the atoms to accumulate to at the metastable level. The metastable state population can exceed the population of the lower level and lead to the state of population inversion. If the metastable state does not exist, there could no population inversion, no stimulated emission, hence no laser operation takes place. Then foundation of laser operation is the existence of metastable state. Light amplification and oscillations. With the active medium in the inverted state, the photon of appropriate energy can stimulate the emission of a cascade of photon, that is the amplification of the light. The initial photon may be looked upon as the input signal, the active medium as the optical amplifier, and the emerging light as the amplifier output. Degree of amplification is measured by the gain, which is the increase in the intensity when the light beam passes through the active medium. Then G is equal to 1 by I into di by dx. Gain is the amount of stimulated emission which a photon can generate as it travels in given distance. For example, if G is equal to 4 per centimeter, it means that one photon produces 4 photons per each centimeter it travels in the medium. Unfortunately, laser material have a very low gain of order of 0.0001 centimeter to 0.001 per centimeter. It means that the photon has to travel a long length of the laser material for producing the laser amplification. For example, if we have a material whose gain is 0.001 per centimeter, if we wish to achieve a light amplification of 1000 times, it is calculated that the light has to travel about 69 meters in the medium. Such a long distances are obviously not practical. However, the important point to note that the amount of amplification increases rapidly with the distance. One of the way of making the light to pass through the long length of the laser medium is by keeping the mirror on both the side of short laser rod or the tube, so that we can achieve the population inversion at a shorter distance. It is not necessary to take the light up to the long distances. At a shorter distance, by putting the mirror on the both the side, we can achieve the amplification of the light at a shorter distance. Then make many passes through the medium, increasing and the effective distance of the travel by the many times. Such an arrangement of the mirrors transforms the simple amplifying medium into a source of light. Although population inversion is necessary for the light amplification, it alone is not sufficient to make the stimulated emission dominate of the other processes. Then according to the Einstein relation, the large stimulated emission, large radiation energy density is required to present a active medium. The pair of mirrors helps to maintain a large radiation density in the medium. A rod shaped laser medium without the end mirror acts as a amplifier. A light beam of the appropriate frequency incident on one end triggers stimulated emission, and amplification output will emerge from the other end, that is done by the optical resonator. What is the optical resonator? A laser very much similar to an optical resonator, electronic oscillator and amplifier tuned to a specific frequency provided with a positive feedback. This is the feedback oscillator where E input, energy input and output. Here B is the coefficient. Low frequency oscillator, feedback using the electric wire. At high frequencies, different kinds of feedback mechanism. Microwave frequencies, cavities completely enclosed in the metal box. Not feasible to the fabricate cavities for use at the light frequency. Dimension should be order of 0.5 mm. Tones and hollow, no necessity for a closed cavity. Open cavity in the form of two parallel mirrors serve the purpose. In laser, the feedback obtained by placing the active medium between the pair of mirrors facing each other. One will be partially and second is fully reflected. The role of the input signal played by the chance photons spontaneously emitted along optic axis of the laser rod. An amplification takes place, which is as photon reflected back into the active medium by the mirror several times, gaining the strength at each passages. And then electronic oscillator is a tank circuit, or we can say it is a resonant circuit to build up a large output with moderate input. In laser, this oscillator is known as the optical resonator or is known as the cavity. The pair of mirrors constitute an optical resonator. There are the two mirrors, one is partially reflected this side and this side is the fully reflected, and this is the open cavity, and amplification takes place in this chamber. And open resonator, that is a fabricated resonator, and this is the, and we can also use the closed cavity. Mirror, plane or curved mirrors can be used in this. Sometimes we use a curved mirror and sometimes we use the plane mirror. Designed such that one reflects all the light that reaches it while other reflects most of the light incident on it. What are the action of the optical resonator? Here we in the C diagram. Successive stages of the action of the optical laser. This is the first stage where active medium in this cavity. This is the reflecting mirror and this is the semi-transparent mirror, and active center is defined here, non-excited state, and the host material is in between the cavity. Now the optical pumping takes place, molecules excited, but it is randomly excited. Now here the stimulated emission takes place, means all the by striking this mirror, all the atoms will move in the, or the photon move in the same phase, and here all are aligned and all are coherent and going back, and here we achieve the population inversion, and here we get the light amplification. And when we get the light amplification, light oscillation takes place, and this partially mirror will transmit the light in the form of laser. This is another diagram based on the similar pattern. Here the high H are high reflectors totally reflecting. Here OC output coupler, or we can define it as a partially reflecting. This is the laser resonator consisting of lasing medium. It may be gas, it may be liquid, or it may be solid between these two mirrors. And lasing medium at the, all the lasing medium at the ground state. The pumping energy, electrical, optical and chemical energy given to that, and then the molecule will go to the excited state and population inversion achieved. At the stage 3, we have the spontaneous emission and stimulated emission will take place. When the stimulated emission takes place, all the atoms and molecules align themselves in the same manner, or all the atoms are coherent and all the photons in the coherent form, and the stimulated emission build up. After that, the full stimulated emission coherent laser beam generated, and the laser beam will be comes out. These are the basic operation of the laser. Thank you.
Dear friends, on that note, you would like to thank Dr. Bansal for coming to our show and delivering this wonderful lecture. And thank you, dear friends, for watching our show. Stay tuned and keep watching. Thank you.